Hello everyone. Today, GWTime is excited to launch our 1500 volts / 320 kilowatt solar MPPT controller, the world's most powerful IP66 rated MPPT controller available today. My name is Zheng Jianyu. Over the past 20 years, I have worked in R&D on UPS systems, wind power converters, solar inverters, and battery storage PCS. I am the founder and CTO of Shenzhen GWTime. In China and Europe, solar installations are growing fast, but the grid cannot always absorb all that power. The solution is to pair solar with battery storage to store the energy when the grid cannot take it and release it when needed. This is becoming a standard requirement, not an option. In developing countries, solar system costs are falling while diesel and gas prices are rising. Solar energy storage microgrids are becoming the main power source, not just a backup. And with the rapid growth of AI, data centers now need on-site solar power as a standard requirement, not just a nice to have. All three scenarios, grid-connected storage, off-grid microgrid, and data center power, point to the same system design. Combine solar, batteries, and smart control into what we call a solar storage DC flexible system. In these systems, DC coupled ESS is becoming increasingly widespread. What is DC coupling? The easiest way to understand it is to compare it with AC coupling. In a DC coupled system, solar energy flows from the panels through an MPPT controller directly onto the DC bus, which charges the batteries. That is it. One step, direct connection. In contrast, in an AC-coupled system, the solar energy takes a longer path. First converted to AC by a PV inverter, fed onto the AC bus, then converted back to DC by the PCS before reaching the battery. 2 extra conversion steps just to charge the battery. The key difference: DC coupling puts solar energy straight onto the DC bus. AC coupling puts it on the AC bus first. The main advantage of DC coupling is higher charging efficiency. As shown in the diagram, in DC coupling, energy goes through only one conversion stage to reach the battery. In AC coupling, it goes through 2 extra stages, the PV inverter's DC to AC stage and the PCS's AC to DC stage. Those 2 extra conversions add over 4% in energy losses. Furthermore, since both the MPPT controller and PV inverter are installed near the solar panels, DC transmission incurs lower losses than AC transmission. Beyond higher efficiency, what about the cost advantages of DC coupling? DC coupling costs less because the MPPT controller is simpler than a PV inverter. No AC output stage required. And because everything connects directly to the DC bus, you do not need AC string cables, AC combiner boxes, or a large step-up transformer on the AC side. These are significant cost savings in a large installation. The grid approval process is also simpler. Overall, DC coupling means lower upfront cost, a clear advantage over AC coupling. The core component of a DC coupled solar system is the MPPT controller. What does MPPT stand for? It stands for maximum power point tracking. Every solar panel has what we call a PV curve, a graph showing how much power it produces at each operating voltage. This curve is fixed by the panel's physical characteristics. When sunlight is strong, the curve shifts up, more power at every voltage. When sunlight is weak, it shifts down. Under any given sunlight level, there is exactly 1 voltage where the panel produces maximum power. At 0 voltage, short circuit, or maximum voltage, open circuit, the output power is 0. Maximum power sits somewhere in between. That peak power point is called the maximum power point, or MPP. It typically occurs at around 80% of the panel's open circuit voltage. The MPPT controller's job is to continuously adjust the operating voltage to keep the panel running at that point, even as sunlight changes throughout the day. By always holding the panel at its MPP, the MPPT controller ensures the solar array delivers its maximum possible energy output at all times. When the battery is full and we need to reduce the output, the controller shifts the operating voltage above the MPP. Higher voltage means lower output power. This is how the system limits charging when storage is full. That is the basic working principle of an MPPT controller. For small systems, the MPPT function is usually built into a combined PV inverter or hybrid inverter. One box handles everything. For larger systems, generally above 100 to 200 kilowatts, the MPPT needs to be a separate standalone unit. It cannot be bundled into the inverter anymore. GWTime launched its first standalone MPPT controllers in 2025, the 60 kilowatt and 120 kilowatt models at 1000 volts. The 120 kilowatt model specifications, 12 PV string inputs, 4 independent MPPT channels with 3 strings each, 55 amps per channel, 120 kilowatts total output, IP66 rated, air-cooled, and only 30 kilograms. Today, we are launching the next generation, the 1500 volts/320 kilowatts MPPT controller. The 320 kilowatt model has 24 PV string inputs and 6 independent MPPT channels with 4 strings per channel. Each channel supports 60 amps. The system voltage goes up to 1500 volts DC. Total rated output is 320 kilowatts, IP66 rated, and it weighs only 60 kilograms. Despite its power rating, it is compact and easy to install on site. The biggest difference between GWTime's MPPT controller and most others on the market, especially the IP20 controllers people are familiar with, is the protection design. Many people who work on solar sites have seen fires, combiner boxes burning, inverters failing, hybrid units catching fire, even DC cables melting. Why does this happen? The grid and batteries are voltage sources. When there is a short circuit, they produce very large fault currents, large enough to blow a fuse or trip a breaker. Solar panels work differently. They are current sources. Their short circuit current is only slightly above their normal operating current. This means standard fuses and circuit breakers do not work well to protect DC solar circuits. For example, if an MC4 connector is not properly seated, it creates a continuous resistance that generates heat. That heat builds up slowly, too slowly for a fuse to respond, and can eventually start a fire. Consider 3 strings connected to one MPPT channel. If one string is wired backwards, the other 2 strings will push current backwards through it. No breaker trips, no fuse blows, the fault current just keeps flowing. Similarly, if an IGBT or MOSFET inside the DC/DC converter fails and creates a short circuit, current flows continuously from the positive to negative terminal of the array through the failed device. Again, nothing interrupts it, and the result is a fire. GWTime's MPPT controller addresses this with software-controlled isolation switches on each input, enabling software-based fault detection and tripping. When the system detects an overtemperature condition at the MC4 connector, a reverse polarity current, or a short circuit fault, it immediately opens that string's switch via software. The fault is isolated before it can cause damage. This is something passive combiner boxes with fuses simply cannot do. With a passive fuse-based combiner box, reverse wiring, backfed current, and short circuit faults downstream all go undetected, and the fuses themselves can become the ignition point. By using GWTime's controller, such fire hazards can be completely eliminated. Beyond input protection, GWTime adds another layer of protection, a software-controlled output contactor. Before every startup, the output contactor is kept open. The controller measures the battery voltage on the DC bus side and compares it to the MPPT converter's output voltage. The contactor only closes when the 2 voltages are closely matched. This avoids a large inrush current when the connection is made. This voltage matching sequence also provides reverse polarity protection on the output side. Specifically, since the cable between the MPPT controller and the battery spans a distance, a wiring reversal would connect the battery's positive terminal to the MPPT's negative terminal, forming a fault loop through the MPPT's internal IGBTs and diodes. This fault loop effectively causes a battery short circuit, generating extremely high currents. The consequences can include blown fuses in the high voltage junction box and welded contactors inside. With reverse polarity protection in place, the system checks the voltage polarity before closing the output contactor at startup. If a reversal is detected, the contactor is not closed, thereby providing complete protection against reverse wiring. Beyond input and output protection, insulation resistance monitoring is another essential feature for MPPT controllers. Why? In a typical distribution network, the transformer neutral is bonded to ground. A 100 kilowatt solar array covers close to 1,000 square meters. With such a large area, if either the positive or negative terminal or any intermediate stage develops a ground fault, a fault current will flow through the path illustrated in yellow in the diagram, potentially destroying the PCS. To prevent this, an insulation resistance monitoring function is essential. In GWTime's MPPT controller, because an output contactor has been added, the contactor remains open prior to each startup. With reverse polarity protection in place, the system checks the voltage polarity before closing the output contactor at startup. If a reversal is detected, the contactor is not closed, thereby providing complete protection against reverse wiring. Many IP20 MPPT controller manufacturers also claim their products have insulation resistance monitoring, but those controllers have no output contactor. Without an output contactor, real insulation resistance monitoring is not possible. In a live installation, the grid's neutral to ground connection passes through the MPPT's output terminals. The moment you try to measure insulation resistance, the ground path is already there. The test result is meaningless. So why do these manufacturers claim the feature works? Because during certification testing, the unit is connected to a test load on the output, a clean, isolated lab setup. Under those conditions, the measurement works fine. In a real installation with a live grid connection, it does not work at all. The feature exists on paper, not in the field. GWTime's implementation works because the output contactor provides true electrical isolation during the measurement. It is a real feature, not a certification checkbox. If you use an MPPT controller without a real output contactor and a ground fault on the solar side, destroys your PCS. The problem is not the PCS. It is the MPPT controller. Choose a controller with real hardware-backed insulation resistance monitoring. Shenzhen GWTime specializes in DC-coupled ESS systems, with all MPPT, BMS, and EMS technologies developed in-house. We also offer standalone solar MPPT controllers and battery-side DC/DC converters in various configurations for individual sale. Some have asked whether GWTime's MPPT controllers are already in mass production. The answer is yes. The photos shown were taken on our production floor, featuring 120 kilowatts and 320 kilowatts units ready for packaging. If you are interested, please feel free to reach out for inquiries or orders. Thank you.